We're nearing the end of our unit on magnetic fields, and we haven't even talked about any numbers yet. We haven't done a single calculation so far. Today is when that changes, with magnetic force. So in 1820, Hans Christian Ørsted was figuring out that current-carrying wires have magnetic properties. They create magnetic fields. And around that same time, working with the same results, a scientist named André-Marie Ampère discovered that two current-carrying wires, because they create magnetic fields, they attract or repel each other depending on the direction of the current flow. So today we're going to develop his formula for the amount of magnetic force that they're exerting on each other. But before we get there, we have to first define some units. Okay, the first one is current. Okay, current is measured in amps, named after said scientist, and 1 amp is defined as 1 coulomb of charge flowing past a point per second. Okay, so 1 amp, 1 coulomb per second, looks like this. Let's say this is our wire. We're going to make it extra large just so we can see what's going on. And these are our charges. So it's electrons that flow. They're flowing that way. So 1 coulomb of charge, remember, is 6.25 times 10 to the 18 ECs. That means 1 amp is 6.25 times 10 to the 18 electrons flowing past a point every second. Now, we do consider conventional current to be the one that we're working with. So we're pretending that it's the flow of positive charge. So though it's really electrons that are flowing, we're going to look the opposite direction at what direction the protons would be flowing. So the first thing that we need to know is how much current is traveling through this wire. The second thing that we need to know is how strong is the field that that wire is in. So the wire is creating its own field, which is interacting with the field that it's sitting in. Maybe it's another wire that's creating a field that this wire is experiencing, or some other sort of magnet. But we need to know how strong is the field it's sitting in, because that field and the current that's passing through the wire itself, those are the two major things that are going to contribute to how much force it's going to experience. There's one more thing, but we'll get there. So the units of magnetic field strength are Teslas, right here. And 1 Tesla is 1 Newton per amp meter. Now, for you, it's not going to be very important that you remember that it's 1 Newton per amp meter. We just need to know that magnetic field strength is measured in Teslas. The third part, it turned out, through experiment, was the length of wire that was in the field. So the longer the wire that was actually in the field, the greater the strength, the greater the force it was going to experience. So the formula that we end up with for magnetic force is FB is equal to BIL. Okay, now some of these letters don't seem to make a lot of sense upon first glance, but B is magnetism. That's the letter that's assigned for magnetic fields. So FB would be magnetic force. Magnetic force. And as all forces are, this one is measured in newtons. This B over here, this is magnetic field. And the magnetic field, the strength of the magnetic field, is measured in Teslas. T. This I is current. And that's in amps, or coulombs per second. And the last thing here, this L, is the length of the wire, and that's in meters. So let's do a quick example here. A 1.55 meter long wire with a current of 5 amps flowing through it is in a magnetic field. The force on the wire caused by the magnetic field is 0.375 newtons. what is the strength of the magnetic field it's in? Okay, so right away we can see it's asking us for what's the strength of the magnetic field. Magnetic field strength is B. Okay, now technically field strength, or technically magnetic field, is a vector. It should have a direction on it. Okay, and so up here in our formula we should be putting a vector symbol on the B, a vector symbol on the force, and a vector symbol on the current. Length is not a vector, it's just how long something is. We're not going to deal with the directions just yet, but we will in just a minute. So B is magnetic field, and that's what we're looking for. It tells us that the length of the wire is 1.55 meters. It tells us that the current, I, is 5 amps. And it tells us that the force on the wire is 0.375, so that's FB. 0.375 newtons. Okay, and so this is just an algebra question, really. You know that the formula we just talked about it is FB equals BIL. Okay, and we are going to plug in numbers and rearrange things. I'm going to rearrange it first and then plug in the numbers because that's what we've been doing. So if I'm looking for the B, it's multiplied to the I and the L, and so I need to divide by I and L in order to get the B by itself. And so I end up with FB divided by IL is equal to the magnetic field. Okay, now we put the numbers in. So the magnetic force is 0.375 newtons. Make sure we have the decimal in there. Divide that by 5 amps. Also divide it by 1.55 meters. And that gets you the magnetic field. Finally, that gives us 0.0484 Teslas. Okay, now I want to visualize what's going on here because this might not be very clear. So in this space over here, let's say that here's our wire, and I'm going to put an arrow on it to indicate the direction of the current. So that's I. I is the current. Okay, now it's sitting in a magnetic field, and for the purpose of our first formula here, we're going to assume that they're perpendicular to each other. So here's our magnetic field. Let's say the magnetic field is contained to being in between these 4 field lines. Okay, so this is our magnetic field, B. The length of wire that's actually in the field is just from here to here. That would be L. Now it's not always going to happen that the field and the current are perpendicular to each other, and so we have to deal with that as well. That we're going to deal with in the fields with angles section next time. Now force is a vector. That means it has magnitude and it has direction. So we figured out how to get the magnitude of it, F equals BIL, but now we need to figure out how do we find what direction the force is going to be. And for that we use right-hand rule number 3. I know you were just hoping for another right-hand rule. So here's how it works. Your hand is open like this. Your thumb is the direction of the current. My current is flowing that way. My fingers are the direction of the magnetic field. Think a field has multiple field lines, and so my fingers are pointing in the direction of the field. My palm points in the direction of the force, so coming out at you like that. Okay, here's how I think of it. Star Wars, Jedi, using the force. The force comes out of your palm. You're pushing something away from you. Okay, that usually helps, so we'll see if that works for you. If you have no idea what Star Wars is, then I'm sorry. Just remember it comes out of your palm. Okay, and so we have a few diagrams going on here. You can see the right-hand rule of using the force, right-hand rule, illustrated on the top right. they're all 90 degrees to each other. Notice that. Current and the field, they're 90 degrees to each other, and the force is 90 degrees to both of those. Okay, that's always how it's going to work. All three are going to be 90 degrees to each other. So when we look at this set of magnets with a wire running through it over here, this is the direction of the force. The magnetic field points from north to south like this. That way. That was a wavy one. Okay, that's the direction of the field. And so then to figure out what direction the current is flowing in, it's either got to be flowing left or right. One of those two. So now if we use the force hand rule, your fingers will point in the direction of the field. Your palm should be pointing upward because that's the direction of the force. And so my thumb is pointing to my right. And so we should end up with a current that's flowing this direction. Okay, that's the current. I. Let's do a couple other examples here. So what is the direction of the force on a wire if the current flows east and the magnetic field is up? Okay, so for me, I'm going to point my thumb east to my right, and then the field is directed up, so my fingers should be pointing up. My palm is then pointing back at me, so that would be south. Okay, so my first example, south is the direction of the force. Second one, what is the direction of the current flowing through a wire if the wire would experience a force toward the east and a magnetic field pointing down? Now some of these are difficult to do when you're sitting, but this one's okay. I have a different one in mind. So the force is toward the east, so that's toward my right, hopefully toward your right as well. The magnetic field though should be pointing down, so it's like this. Okay, in that case, the direction of the current should be pointing toward you. That's your thumb. Pointing toward you, that's also south. Okay, so both of these end up being south. And finally, we'll do one example that puts it all together. A wire is 1.25 meters long and has a current of 3.25 amps north flowing through it. The current carrying wire is in a magnetic field with a strength of 0.465 Teslas up. What is the magnitude and direction of the force exerted on the wire? So we're going to do the calculation part in a moment, but let's just do the direction part right away because we just learned about that. So it says that the current is flowing north. So I'm going to point my thumb away from me. I don't know how everything else is pointing right now, but we'll go with that. It says that the magnetic field strength is up. Well, there you go. What is the magnitude and direction of the force exerted on the wire? So I'm holding my hand like this. That means that the force is going to be directed toward my right, which is east. Okay, so the direction, I'm going to write that part down already, is east, and that's dictated by the right-hand rule. Now the rest of it is that F equals BIL calculation. So we're doing magnetic force, this is a vector, equals BIL. The B has a direction and the I has a direction. We've already figured out the direction of what the force is going to be, so we don't need to worry about that anymore. So our force is what we're calculating. So we don't even need to rearrange anything. The magnetic field has a strength of 0.465 Teslas. The current is 3.25 amps. And the length of this wire is 1.25 meters. Okay. So when I put that all together, I get 1.89 newtons. and we already figured out the direction was east. So each of these force calculation questions is going to have two parts to it. It's going to have the numerical calculation, calculating the magnitude of the force or whatever other piece you're looking for, and the second part is always going to be using the right-hand rule to figure out what the direction of that missing piece is.